Now we'll learn about vectors. Vectors are very important for physics, so this is something that you'll be using throughout the course, so it's very important that you understand vectors. The first thing we're going to learn about here are vector scale diagrams. This is a good method for learning vectors. It's not as practical for solving some later vector problems you'll have, so I won't focus on this too much. You can kind of read this slide. The definition here isn't too necessary to copy down, but there is examples in the book on using vector scale diagrams. If you're having trouble, it might be worth going through that to understand it a bit more. But I won't cover it too much. I don't want to. I know we're working really diligently, and it's a support that some people might need, but I don't think we need to focus on it too much at this time. So what is a vector? A vector can be represented by a directed line segment, and it is a direction of a quantity. So we might have something like a speed, which is a scalar quantity, but as soon as we assign a direction to that scalar quantity, we now have a vector quantity. And the vector itself is a directed line segment that shows in which direction, usually with an arrow, the quantity is being directed towards. The vector itself is a straight line, and quite often the length of the line is used to represent the magnitude of the vector. A very long line implies that it is a very large magnitude measurement or quantity we're looking at. A very short line implies a very low value quantity. Vectors, one end has an arrow, that's called the tip, and one hand is where the arrow starts, that is called the tail. So that is something else to refer to, the tip and the tail of a vector. Now again, with the vector scale diagrams, we'll look at it here with a simple kind of one-dimensional vector scale diagram. Back at our previous question where we had the distances between the schools and the mall and the library, you might see some of those measurements come up again. But here we have two displacement vectors. One is 700 meters west, one is 500 meters west. When we add those two vectors together, we end up with 1,200 meters west. If we are adding vectors using a vector scale diagram, we draw the tip of one. Sorry, we draw the tail of one vector at the tip of the other, and then we connect the line from the tail of the first vector to the tip of the second vector. So that's what you're seeing down here. Now again, it says here in most cases you won't use a vector scale diagram. I've already kind of talked about that. Let's look at a practice problem. Here it says Fred is going to visit a friend, but he needs to stop at the variety store first. He walks 200 meters north, and then he walks 600 meters south to his friend's house. Now they're asking to do a vector scale diagram. It's on the side. I won't really go through it too much, but we will discuss what his displacement is. I think it goes on to the next part of this question. So what is Fred's total displacement? He's traveled 200 meters north and then 600 meters south. So his total displacement would be the addition of those two displacement vectors. 200 north plus 600 south. Well, we would have to consider, or we could consider the north as negative in this case. So it would be 600 meters south plus negative 200 meters south, or and then that would be 400 meters south. And what is the total distance that Fred travels? Distance again is the sum of the distances. So here his distance traveled would be 200 meters plus another 600 meters, so his distance would be 800 meters. This one I'd like to do on the paper with you. It says here we have a rabbit that goes 3.9 meters north, nibbles on some grass, and then it hops 6.3 meters north. It says to sketch a diagram of the motion showing the displacement vectors and the total displacement vector. So just for just so we're fully aware of that. Its first set of motion would be here, which would be 3.8 meters north. The second vector might be like this, and this is not to scale, 6.3 meters north. Its total displacement would be from here all the way up to there. I'll draw that vector on the side. And this total displacement vector would be the sum of the two, which would be, let's see, that would be 10.1, I believe. 10.1 meters, and my displacement direction would be north. And when we're asked to calculate the displacement, we have 10.1 meters north. The next question says a skateboarder slides 4.2 meters up a ramp, stops, and then slides 2.7 meters down the ramp before jumping off. Let's do this without sketching the diagram. We'll just go straight into the question here. So it says, what is his total displacement and his total distance? So if he's traveling, just a second here because I want to see. If he is traveling, I can't see the problem. I have to move my computer around my screen. So it said he goes 4.2 meters up the ramp and then slides 2.7 meters down the ramp. The distance he travels is the sum of those two distances. So distance 1 plus distance 2. Distance is 4.2 plus 2.7. And that works out to 6.9 meters. The displacement would be delta D. Let's say it's, so he goes 4.2 meters up. So let's do it this way, where we add the displacements. Sometimes you have to decide on what is better. Do you add the displacements or do you subtract the positions? So here I am adding the displacements together, and I have to move my camera over. My first displacement is 4.2 up. I'll put a U for up. My second displacement is 2.7 down. And I will say, let's say up is positive. That means I can rewrite this without the directions. 4.2 plus negative 2.7. And 4.2 minus 2.7 is 1.5 meters, and we're left with the direction up. Let's look. I think there's two more problems here. So now we're going to get into some other types of vectors that are not all acting in the same direction or in the same dimension. Here we have a question that says determine the x and y components of the following vectors. Okay, so in this case, let me draw out this vector for 4a. It is 5 meters per second. Sorry, it's a distance or a displacement, so it's 5 meters north and then a 37-degree turn towards the east. So I will make a little wind rose here. North, south, east, west. And if I am having a displacement vector or a distance vector like this, a displacement vector, 5 meters per second, so I would be traveling essentially north and then making a 37-degree turn towards the east. So it'd be something like this. That's not the best 37-degree angle, but we don't have to be accurate in the sketch. Now, in order to find out what this vector here, this 5.0 meter vector, is when it's written in the y direction here, we would have to find out how we can span this along there. And what you might notice, I've just kind of closed this off as a triangle. You might notice this is a right angle triangle. And what you might remember from trigonometry, is that if you want to span a hypotenuse onto an adjacent side, it's the same as doing that hypotenuse times the cosine of that adjacent side. If you want to find out what the opposite angle is, it's the same as doing the hypotenuse times the sine. So in this case, to find my Vx, I would write down 5.0 times the sine of 37 degrees. And for my y, it's the same as 5.0 times the cosine of 37 degrees. The sine of 37 degrees, it finds this adjacent side, it finds this opposite side, which is in my x component, that's my east component of this vector. The cosine finds this side here, which is my y component. So let me share my calculator with you here so that you can see just how I calculate this as well. Oops. Okay, so 5.0, you don't need to necessarily do that, but multiplied by the 37 sine equals 3.009. So when I do that, I have my Vx equaling 3.0 meters, and I know this is directed towards the east, so I write down my direction east. To do 5 times the cosine of 37, I end up with, equals 3.99, which rounds up to 4. And that is meters, and that would be towards the north. So that's how I would break up this vector, this 5 meters north, 37 degrees east, into components. It is made up of a Vx and a Vy. The Vx is 3.0 meters east. The Vy is 4.0 meters north. So these are important, so we'll do another one. Let's look at 4b. For 4b, it says 13 meters per second, and that is 13 meters per second would be a velocity vector. So it is directed west 67 degrees south. So in this case, let me start here. Can we see that point? Yeah. So I would be going mostly to the west, and then make a 67 degree turn towards the south. So I'd end up somewhere like here, like this. This is my turn. This is a 67 degree turn. To break this vector up, which is 13 meters per second, my Vx, and I guess in this case I should have put dx. This is a displacement vector, so these are dx's and dy's. My Vx in this case would be, I would need to do the cosine to span this 13 along this side here. It would be 13 cosine 67, because the x direction is adjacent in this case, whereas in this case the x direction was the opposite. Opposite refers to sine. Here it's adjacent. Adjacent refers to cosine. So this is 13 cosine of 67 degrees. And I might as well write down what my y is going to be. It would be 13 sine. It's going to be this length here. 13 sine of 67 degrees. We'll do that calculation here. So 13 times 67 cosine is, let's hit the equals button, 5.0 7. Should be 5 right on the dot, but it's just because of the 67 is not exact. So that is 5.1 meters per second. That's directed towards the west, and 13 times 67 sine is, it'll round up to 12 meters per second, and that is south. Okay, so let me clean up the screen a bit here, and we'll go on to, oh, that's it. So that's it for this lecture. It's important to understand this kind of breaking up a vector into components. We'll be doing it quite a bit, and you'll see it in some of the later questions that we do in some later lectures.